All right, hello everyone. I have quite a lengthy question here for us to look at. It takes into consideration quite a couple of ideas regarding this topic that we are discussing. Um, and the idea here is we're going to construct an electrochemical, a voltaic cell, and then do a whole lot of calculations and look at a couple of aspects for it. So we're given two half reactions written in their reduction form. So we've been looking at the reduction of nickel and looking at the reduction of cadmium. And then we're asked a couple of questions for this cell. All right, so let's just start with it, and then we'll look at each of the finer aspects. So the first point is we need to diagram the cells. In other words, we need to draw a diagram for the cell and label each of the components, including the anode, the cathode, and the salt breach. So the best way to do this is if we look at the standard standard reduction potentials for each of these reactions, we see that nickel has a value of minus 0.25 volt, and the cadmium reduction has a standard potential of minus 0.40 volts. So in terms of where they are relatively to each other, it means therefore that nickel is located above the cadmium reduction reaction, right? So that therefore it means that nickel would preferentially be reduced rather than what cadmium would be reduced. So therefore nickel is a stronger oxidizing agent than what cadmium is, right? So if nickel is a stronger oxidizing agent than what cadmium is, it means it's the one that's more easily reduced, and cadmium is the one that is more easily oxidized, right? So it is the species that will undergo oxidation. It's the stronger reducing agent. Cadmium is oxidized, stronger reducing agent, lower on the potential table, and nickel is the stronger oxidizing agent, more easily reduced, higher on the potential table. So the species that is reduced, right? So in other words, the nickel in this case, of course, will form our cathode. The species that is oxidized will form our anode. All right, and that's how you figure it out. So anode is the species that undergoes oxidation. It will be the species that is the stronger reducing agent. All right, it's a species that wants to undergo oxidation. The cathode will be the stronger, is the species that wants to undergo reduction, so it's the stronger oxidizing agent. All right, and that's how we make those choices, well, based on our reduction potential table. All right, cool. So now that we've discussed that, we know which reaction needs to go where. Let's draw a little diagram for our cell. So there we have that. And let's draw each of our beakers over there. All right, and let's put, I'm going to put the cathode. So on the left hand side, we put our cathode. Right, and at the cathode, of course, reduction occurs. And our anode is on the right hand side, and it's the electrode where oxidation occurs. All right, good. Now the next question is, what electrodes need to be placed? So right at the cathode, we said it's the nickel electrode, so that means we need a solid nickel electrode here that we will make use of. And just for the sake of it, let's make cadmium. Cadmium is probably, a better electrode color to use is probably something like a yellow or an orange, but that's going to be our cadmium. Okay, and these are solid electrodes, electrodes. So this is nickel solid, and this red one is solid cadmium. I'll put it there. Cadmium solid. Okay. Right. Remember, this is just a diagram, so it's not exact. I mean, it's not how it's going to really look in real life. This is just to get a broader understanding of that. And these solid electrodes need to be connected, of course, by some sort of a wire, right, that connect them in some kind of a manner. And in the beakers themselves, we of course need a solution. So in the solution, if we look at the other species involved, the nickel of course needs to have nickel 2+ ions, and the cadmium of course needs to have cadmium 2+ ions. So nickel is in a nickel 2+ aqueous solution, and the cadmium is in a cadmium 2+ aqueous solution. So there's some sort of cadmium salt that you dissolved to get the cadmium 2+ solution, and the nickel you dissolve some nickel 2+ salt to get the nickel solution. Alright, the question now is, we still need something that's going to allow us to complete the circuit. So yes, we still need a salt bridge. So let's draw in a salt bridge. Alright, is that, oops. Let's just give it enough space so that I can actually draw. So there's our salt bridge. Alright, and in our salt bridge we need some sort of electrolyte, something that's going to help shift or to conduct the complete the circuit, and also create the charge balance that we need as the reaction, the reaction proceeds. So let's place here sodium nitrate. I mean, you can use potassium nitrate, whatever you want to put. So just put sodium nitrate in the salt bridge as our electrolyte. All right. Some other things that we can include in our diagram, right? The reduction reaction is, of course, nickel 2+ aqueous being reduced, so it's gaining 2 electrons, and it's being reduced to nickel solid. And because it's being reduced as nickel solids, in other words, these nickel 2+ ions are being reduced to nickel solids. In other words, this electrode is going to gain in mass as the reaction proceeds. And the little important point of, so like physically what's going to happen as this happens in this salt bridge to maintain charge balance, therefore it means that our sodium plus ions in the salt bridge are going to have to push down through the salt bridge, right, as these nickel 2+ ions go towards the electrode to be reduced. The sodium will have to proceed through the salt bridge into the solution to maintain the charge balance. Right. Also importantly, for this reduction to occur, that means the nickel electrode where the reduction occurs is the electrode where we require the electrons. So this gives us the direction of electron flow in the circuit, right? So the electrons need to flow from the cadmium electrode to the nickel electrode. And that just leads me to the next point in terms of what needs to happen at the cadmium electrode. At our cadmium electrode, we of course need oxidation. So that means our cadmium solid needs to form cadmium 2 plus. I can move this a little bit to the right. Cadmium 2 plus aqueous plus 2 electrons. Right, so it needs to produce electrons so that they can flow through the circuit to the nickel electrode, where they allow the nickel 2 plus to be reduced to nickel solid. So hopefully you can see that our cadmium electrode is going to be used up over the course of the reaction, or over the course of, let's call it the reaction. And therefore, eventually that electrode is going to disintegrate and be completely dissolved into the cadmium solution, and the nickel electrode is going to gain in mass. Also an interesting situation in terms of what is needed here for mass, or for charge balance, in terms of what the salt bridge does, right? Because we have electrons flowing out of the system, and we have cadmium here forming cadmium 2 plus, right? Let's just do it in the right color. We have cadmium forming cadmium 2 plus, in other words, forming a positive species here in this solution. Our salt bridge has to balance that by providing the NO3 minus ions, right? So these NO3 minus ions will start moving into the cadmium electrode solution to balance that charge in this solution. Right, and that's the functionality of the salt bridge. That's why it allows for the completing of the circuit, but it also provides the charge balance. So that's, so in one principal way, that's how it completes the circuit. So it allows charge to flow. So the flow of charge is by the NO3 and the sodium plus to move through the salt bridge, and some of your other ions to start moving up in the salt bridge. But that's in principle what's actually happening here, is to balance those charges. That's what they are doing. So in this case, so that's what's happening. Other notes that we can make for ourselves is, in terms of, we should remind ourselves what are the polarities of these electrodes. So the place where the electrons are generated is of course the anode, and that means that this electrode has a negative polarity, meaning because it is where the electrons come from. It's the source of our electrons in the circuit. Right, so that means the electrons are being generated here because of the oxidation reaction. That makes it negative. And the cathode has a positive charge, a positive polarity, because the electrons are being consumed at this electrode, right? So as you can see, because of the reduction reaction, the electrons are consumed. So positive polarity, electrons are consumed. And a negative polarity at the anode, because electrons are produced. All right. So I think that's enough of the diagram. We've labeled everything that we need: anode, cathode, and salt bridge. We know where everything needs to go, what reactions need to happen where, how the electrons flow, and what reactions happen where. All right, so that's the main points, and we've done it diagrammatically, so we know exactly what our setup is. Okay, so now we can look at our next question. It says to use the equations for the half reactions to write a balanced net ionic equation for the overall reaction. All right, so that shouldn't be too challenging, because we've already identified which reaction needs to undergo oxidation and which reaction needs to undergo reduction. So our oxidation half reaction is of course the cadmium reaction, cadmium solid needs to proceed to form cadmium 2 plus, aqueous plus 2 electrons, right, oxidation, and our reduction half reaction is nickel 2 plus, aqueous plus 2 electrons, forming nickel solid, right? Of course, the oxidation reaction occurs at the anode. The cathode is the reduction reaction. And if we sum those together, we see, right, we only need one of each of these. So the factor that they need to be multiplied by is 1 in each case, because they already have 2 electrons, right? So 2 electrons are being transferred, so we don't need to balance them by any factors. So then we end up with cadmium solid plus nickel 2 plus aqueous, and that will produce cadmium 2 plus aqueous plus nickel solid. All right. So that is the balanced, full balanced reaction for that we needed to look at, right? So that is the net ionic equation for the overall cell reaction, right? So that is what we wanted to write. So we can see that nickel is being reduced, cadmium is being oxidized, all the species are in their correct phases, and that's what we wanted to do. All right. Let's look at C. C says, what is the polarity of each electrode? All right, and we've actually already done that in our diagram. So let's just write it down again. So our anode, right, is negative. And why? Because the anode is negative because that is this place where electrons are being reduced because of the oxidation reaction that takes place at the anode. So electrons are being reduced, are produced there. And if they're produced there, then that makes that electrode the negative electrode. It gives it a negative polarity. All right, and in parallel to that, or in opposite to that, our cathode will have a positive polarity because that is the electrode where the electrons are being consumed to assist in the reduction reaction, the reduction half reaction. All right, so that gives the cathode a positive polarity. Cool. Moving on to D, it asks, what is the value of the standard cell potential? All right, so to calculate E naught cell, we must use the cell potential of the cathode minus that of the anode. Right, so it's basically the standard cell potential is the final potential minus the initial potential, right? So it's where the electrons start, so meaning at the anode where they are formed, minus what their potential is at the cathode, so where they end up. And that's just the difference between them. So for this specific situation, we looked their values up earlier. I wrote them down. So at the cathode, they are minus 0.25, and at the anode, it's minus 0.40 volt. So this is minus 0.25 minus 0.40, and that gives plus 0.15 volt. All right, and just some interesting things. So that's our E naught cell. This is of course means that we have a product favoring equilibrium. All right, and it means that our voltaic cell can generate electrical energy, right? As we want it. That's because we chose the correct setup for it, so that we ensure that the species that wants to undergo reduction, in other words, the species that is the stronger oxidizing agent, is placed at the cathode, and the species that is the stronger reducing agent, in other words, the species that wants to undergo oxidation, we place at the cathode, the anode. Right, so we set up the cell as such so that we ensured that we would get a positive value for the cell potential, for the standard cell potential. Right, because this, so that we get a positive value for this, so that we have a product favoring equilibrium. All right, so yes, this makes perfect sense and forms a perfect and coherent picture at the moment. All right, so we can look at the next part of the question. It now asks, in which direction do electrons flow in the external circuit? And of course, we've already done that, in that the electrons will flow from our anode, where they are generated, to the cathode, where they are consumed, right? So you can just write that as part E. They will flow from our anode to the cathode. All right, and I mean, our reason for that is they're generated at the anode and they're consumed at the cathode, and that's why they flow as such. Cool. Okay, so let's look at F. And F now asks us to elaborate a bit on how the salt bridge works. So it says, assume the salt bridge containing sodium nitrate connects the two half cells, right? So that's why I chose sodium nitrate, because it's what's, I knew that F was the question that comes. And it says, in which direction do the sodium aqueous ions move, and in which direction do the nitrate ions move? And that's also something we've already discussed, in that the sodium ions need to move into our cathode compartment, and our nitrate ions need to move in our anode compartment to maintain neutrality in the half cells. But let's perhaps elaborate a bit onto that, because in a broader sense, what's really happening in these cells. So maybe let's draw a picture a bit further down here. So what's happening in each of these half cell compartments? So all we need really is the little bits. So that's what the salt bridge looks like in here. So you have nickel 2 plus, and you have sodium plus in here, and we had our nickel solid there, and our other half cell compartment, of course, it had the cadmium. Ooh, that's terrible. It had the, why on earth? Okay, that's fine now. So there we have the cadmium, and we had cadmium 2 plus, right? As well as, in this case, the salt bridge was pushing down the nitrate. That's what we were saying. So in this case, the sodium was entering, in this case, the nitrate was entering. And the reasons for this will become apparent right now. So the question is, how do you get nickel 2 plus into solution here? Well, you probably have to dissolve something like nickel nitrate. And to get cadmium 2 plus here, you probably have to dissolve something like cadmium nitrate. I'm just using that to make it a bit easier. So technically you have cadmium here, and you have nitrate ions, and in this case you also have nickel here, and you have nitrate ions. Okay, so remember, you have to dissolve a salt, and you put the electrode in the salt mixture, in the salt solution, and you put the cadmium into the salt mixture, and then you connect the salt bridge, and then the voltaic cell can work. All right. So now to maintain neutral conditions in both of these half cells, we need to think about how these ions move. So what happens at our cathode? Well, our nickel 2 plus ions, so let's remove that arrow, our nickel 2 plus ions are reduced to nickel solid. So that means that the positively charged species in our cathode go from solution to the solid phase. Right, that in principle removes a positive species from solution, right? They combine with the electrons to form a solid. And what does that cause? That in principle causes a sort of a charge imbalance, if you want to, or not a charge imbalance, but you can just think of it as these nickel 2 plus ions flow towards the electrode, they reduce, they form nickel solid. This means that the sodium plus ions in the salt bridge want to start flowing out of the salt bridge into the solution, right? Because they want to replace the positively charged species in the solution. All right, inherently, what this also wants to do is it pushes up this nitrate ion in there, because it wants to then keep the charge neutrality, right? And that completes the circuit actually, because it allows for this continuous flow of the charge. So this nickel nitrate salt that dissolved means that those ions can exchange. The sodium ions go into solution because the nickel 2 plus are being removed from solution. They go to the solid phase, and the sodium ions come into solution. The nitrate ions that are in solution start moving into the salt bridge. All right. The reason those nitrate ions also move into the salt bridge is because the nitrate ions that are currently in the salt bridge come out of the salt bridge here at the anode side. And why do they want to come out on the anode side? Well, because they are trying to maintain charge neutrality at the oxidation half cell, at the anode half cell, right? Because they need to move into this compartment because cadmium 2 plus ions are being produced, right? Cadmium here is going from the solid state to cadmium 2 plus, right? That is what's happening at our anode, right? And while that is happening here, these cadmium 2 plus ions that are in solution start then pushing up into this salt bridge here. So again, you have that exchange of the positive and the negative ions into the salt bridge. And in principle, actually, that's what pushing the sodium ions out on the other side. And that's actually how the charges flow completely. So that allows for the electrons to flow. The electrons flow. These positive charges here flow up in the salt bridge here. The negative charges flow out here. Positive charges flow out here. Positive charges flow up there. Negative charges flow in here. Negative charges flow out there. Negative charges flow out there. Negative charges flow in here. You can see how all the negative charges flow in one direction, and all the positive charges flow in the opposite direction. All right. And I mean, it's a very nice little picture. How you can just see how they try to balance each other out the whole time to ensure that A, there's a charge, so the charge flows, and B, the salt bridge just allows to keep charge neutrality in the compartments so that the charge can actually flow. All right. If this doesn't make too much sense to you, then that's actually okay. I mean, that's not the end of the day or the end of the world. The more important point is which species pushes into what solution, and at the cathode the positive species pushes in the sodium, and at the anode the negative species pushes in the NO3 minus. Alright, so that was question F. Alright, good. So looking at question G, it says calculate the equilibrium constant for the reaction. Alright, so to calculate the equilibrium constant, of course, we can use the standard cell potential. So there's a relationship between those two parameters. So E naught cell is equal to RT N, and then the Faraday constant ln K. All right, and so we can solve for the equilibrium constant. So K is equal to E to the power N F E naught cell over RT. All right, so it's just in terms of an easier notation, it's exponent of all those values. Right, and then we can put it all together. So N is the number of electrons transferred, the number of the number of electrons transferred, and we know that is 2, right? Because of our balanced reaction equation, we know we need 2 electrons to be transferred in this redox reaction. The Faraday constant has a value of 96485 carbon per mole, and this is of course not carbon, sorry, coulomb per mole electrons. So coulomb per mole electrons, and that will cancel with the number of mole of electrons that need to be transferred, which is 2. Our E cell has a value in volt, but which we calculated, so 0.15, so 0.15 volt, and that is in joule per coulomb, right? So a volt is similar or as the same units as joule per coulomb. So a volt is 1 joule per coulomb. We use R as 8.3145 joule per Kelvin per mole. Okay, and then T is 298.15 Kelvin. All right, because we're looking at standard conditions, so it's 25 degrees Celsius, 298.15 Kelvin. And then you should get a rounded value here. So 2 significant figures for the E cell, which is in 2 significant figures of 1.2 times 10 to the power 5. And as you can see, right, so just some interpretation, as always, this is a value that's much larger than 1, right, which is as expected. We expect this value to be larger than 1 because our E naught cell is positive, indicating that we have a product favoring equilibrium. All right, and that is as we expected. This also indicates K is much larger than 1, indicating a product favoring equilibrium. Okay. Okay, so let's look at question H. So question H now says, what happens if we were not at standard conditions? What is the value of E cell? And if we change these conditions, is the net reaction still as we had it in question B? So in other words, is this still the forward reaction? So let's look if we use the Nernst equation. So GH, what happens with E cell? All right, so the Nernst equation says E cell is equal to the standard cell potential minus RT N F ln of Q. All right, and we can write Q for this reaction, E naught minus RT in Faraday constant, because Q is for this reaction, right? So Q will just be dependent on everything that has a concentration. So if we look at the products, the only thing that has concentration is this ion. Nickel solid will have a value of 1, and nickel 2 plus will be in the reactants. The solid will also have just a value of 1, right? So then this would be the concentration of cadmium 2 plus, and this would be the concentration of nickel 2 plus. All right, so E naught cell we've calculated as 0.15 minus R is 8.3145 joule per Kelvin per mole. T is 298.15. N is of course the number of mole of electrons transferred, that's 2, and F is 96485 coulomb per mole electrons. All right, and then ln of Q, so those are the values that we're given. So we're told the concentration of nickel is 1 molar, and that of cadmium is 0.010 molar. So the cadmium 0.010 molar, and nickel is 1.0 molar. So how does that change the value of the cell? Well, I get here a value of a very nicely rounded value of 0.21 volt. All right, so what do we see from that? Well, E cell is still positive, right? So E cell is still larger than 0. So that means the reaction is still spontaneous. As written. Therefore, the forward reaction is still favored. Right, because a positive value for E cell means that the forward reaction is spontaneous, or meaning this reaction is going to be spontaneous until equilibrium is reached. In other words, until the battery is flat for these conditions. So that means this is fine. This is still the reaction that is occurring, and it kind of makes sense. I mean, there's still reactant at the moment here, so there's still 1 molar of nickel. There's still some of the cadmium, or little of the cadmium present, so meaning that there's still a lot of nickel that can be reduced, and it seems to be that this reaction is still happy to occur as it is. So meaning under these conditions it is good. So this is the forward reaction. The reaction is still occurring as written. Okay, good. So that was question H. We can move on to the last question, which is question I. Right, so question I says if 0.05 ampere is drawn from this battery, so in other words this cell, how long can it last if you begin with 1 liter of each of the solutions, and each was initially 1.0 molar in dissolved species. Each electrode weighs 50 gram in the beginning. Okay, so what we're told is that you have an electrode where the concentration of each of these species are, or the reacting species, that's the important word. So in other words, you have 1 molar of a 1 liter solution of nickel, and you have 50 gram of cadmium. All right, and how long will this be able to last? So our answer is to look at our chemical equation that we wrote. So it means we have 50 gram of cadmium, and we have 1 liter of a 1 molar solution of nickel 2 plus. So, and then how long would this be able to last if 0.050 ampere is drawn from this. And hopefully that you see as well, we have a chemical equation that's dictating to us the number of mole required of each of these species. So the first problem is a limiting reactant problem that we can solve. Then the second problem is from there is to determine, once we know what the limiting reactant is, in other words the number of moles, we can relate that to how many electrons this limiting reactant is able to provide in total. So now how many electrons is physically captured in either 50 gram of cadmium or in 1 molar in 1 liter of nickel 2+. So meaning how much is actually available in a solution such as that. And then once we know that, then we can relate that to for how long is something able to draw a current of 0.05 ampere. All right, so those are the steps in our problem here. So, and this is question I. So if we look at our chemical equation, we say cadmium solid reacts with nickel 2+ aqueous to form cadmium 2+ aqueous plus nickel solid. Right, and we're told that our nickel 2+ species, let's just call it nickel 2+, has a concentration of whatever the volume is of nickel 2+ times the concentration of nickel 2+. And we're told we have 1 liter of this solution and it has a concentration of 1 molar. So that means we have 1 mole of nickel 2+. On the other hand, the number of mole of our cadmium solid we can calculate from the mass divided by the molar mass of cadmium, and we're told we have 50 gram, 50.0 gram. The molar mass of cadmium is 112.41 gram per mole, and that gives us 0.444 mole cadmium. So because these two species react in a 1-to-1 fashion, right, we can clearly see that the cadmium is our limiting reactant in this case, right? There's 1 mole of the nickel 2+ and there's only 0.44 mole of the cadmium. All right, so therefore the cadmium is the limiting reactant. It also makes sense. It's in principle the reactant that has to provide the number of electrons because it's the species that's being oxidized. So logically it kind of makes sense. So the question now is, how many moles of electrons can 1 mole of cadmium provide? And for that we return to our original oxidation equation. So 1 mole of cadmium can provide 2 mole of electrons. All right, so where's my pen? So 1 mole of cadmium can produce 2 mole electrons. So the number of mole of electrons that we obtain from 0.44 mole of cadmium can be related to the number of mole of electrons using a sort of conversion factor. So 2 mole of electrons for every 1 mole of cadmium, and that is then equal to 0.88 9, and so on mole of electrons. All right. So now we know what the number of mole, the maximum number of mole of electrons that this can be produced from 50 gram of cadmium. We can calculate the amount of charge. So we need to convert this to a Coulomb amount. All right, so what is the amount of possible charge that this can generate? And therefore, this is the quantity Q, right? So Q is equal to this number of mole of electrons multiplied by the Faraday constant. Because the Faraday constant gives us the quantity of how much charge, Coulomb, is in 1 mole of electron. So 0.889 mole electron is in 96485 Coulomb per mole electron. And this gives me a value of 85833.11 Coulomb. All right, so that's how much charge is carried in, or is possibly can be possibly transferred by 50 gram of cadmium. So now the final question is, for how long can this a current of 0.05 ampere be drawn from this? And if you think about what is a current of 0.05 ampere, so a current of that 0.050 ampere, an ampere is a value of a certain amount of Coulomb per second. All right, and currently we know how many coulombs, what the total charge is. So we can calculate the time from this. So right, the relationship between current, time, and charge is, if you want to make a big note for yourself there, is that current is equal to the amount of charge divided by time. So time is equal to charge divided by current. So that means we take our total charge, Coulomb, divided by this 0.050 Coulomb per second, and this will give you a rounded value of 1.7 times 10 to the power 6 seconds. Or, I mean, that's a weird number to look at. So this is 480 hours.